Okay, so with inverse trig integration, we have formulas, just like how we did with the derivatives. We have these formulas. Yes, it's 2 more formulas to know. You don't need to memorize these formulas today or anytime really soon. You just need to know when to use which formula and how to use it. So we're not going to approach these as normal U substitution, okay? We're going to kind of incorporate what we already know, but then it's always going to go back to these 2 formulas. So just jumping into the first example, which formula does example 1 look like? Arcsine. Okay, so it looks very similar to this, almost identical. So if you look at this, you can figure out what A should be, what U should be, and what DU should be. This is how we're going to do this. For some people, what I'm doing is going to be a little overkill. You're going to be able to do this without writing all this out. But first day we're doing it, it's not going to hurt anybody to write this stuff out. So the A is always the number. So, and we can see here, there's a 4 in place of A squared. So what is just A? 2. Okay. In place of U, there's an X. So in this case, U is just X, so this is not like normal U substitution, right? This is using a formula. And then DU would be DX. Okay, so let's replace all of that stuff. So I'm going to replace the DX with the DU. I'm going to replace the 4 with an A squared and the X squared with the U squared. If you notice, what I have now looks exactly like this formula. Okay, so this is going to equal, just using the other part of the formula, arcsine of U over A plus C, just using the other part of the formula. And then just like when we did U substitution, although this is a little bit different, we are going to just replace the U with an X and replace the A with a 2. Okay? Now if you feel like you can go straight into the answer, that's great. You don't have to show all of these steps. So A squared is in the formula, and since 4 is A squared, A is just 2. The only thing I don't like really about these problems is that you can't, you know how like normally when we integrated, I would say, how do you check your work? And you would say, derive it. If we try to derive our answer, it will not really look exactly like what we started with. It'll be equivalent, but it will be very difficult to check that way. All right, so let's look at example 2. You can see that this is different. There's no square root. There's not a minus. There's a plus instead. It looks very similar to that formula. So once you've kind of identified whether you're using arcsine or arctan, you're going to go off to the side and you're going to do A, U, and DU. All 3 things. A is always a number. U is always a function of X. So what do you guys think A should be? Square root of 2. If you don't have a perfect square, you know, like over here we had 4, here we have 2, we still got to square root it, because A squared would be 2. All right, what about U? 3x. And then du here would be 3 dx. Now what did we normally do with U substitution in this 3? We divided that thing over. We're going to do the same thing here. The derivative of 3x is 3. Okay, so looking at what we have here, I have a 1, the 2, that's the a squared. If you're like, I don't think I need to do all this, I think I'm good to go to the next step, you are correct then, you are. And don't let this confuse you that the du is off to the side instead of the top. It means the same thing. So just using the other side of the formula, I'm going to rewrite 1 over a arctan u over a plus c. So it's like transforming what we have into the first part of the formula, and then writing the second part of the formula, and then saying, okay, well, what does this mean for our a, u, and du? So we have a 1 over 3. A was root 2, so I'm going to go 1 over root 2. Arctan 3x over root 2 plus c. So it's weird, but it's really just using a formula. It's not like exactly like what we did with other u substitution. Okay? All right, so number 3. What's different? There's E. Do you think I could get this to look like one of the two formulas? If so, which one? I think I could probably get this to look like arcsine. I want to show y'all something though really quick. Don't write this down, just watch this. If a student just walked in and they didn't even know about those two formulas and they were trying to integrate this problem, they would probably let u be the denominator. Don't write this. Just watch. And then du would be negative e to the 2x times 2 dx. And you see how this is not matching up to here? It's not the same. So that's how I know this was not a good u. That's why I was telling y'all not to write this. Okay, so that's kind of how you know you try something and it doesn't work. But now we know, we see a square root, we see a minus, we think this might be arcsine. It does end up working because if you think about e to the 2x, that's the same as e to the x squared. So I do have something squared minus something squared. And this e to the x on top, I'm just hoping it'll wash out here with what we have next. It's okay to hope in math. If it doesn't work, I'll just have to try something else. You're not always going to know exactly how the problem's going to play out when you look at it. So what's my a? 1, or square root of 1. And then the u here, I can see that now this is just e to the x, because it's u squared. So what would du equal? What's the derivative of e to the x? E to the x dx, which, good for us, is sitting right here. So let's make this look into the first, make this look like the first part of the formula. The e to the x and the dx, we're going to replace that with the du. Bottom is going to be square root a squared minus u squared. You can look up at the top in the box to see that this is arcsine of u over a plus c. This, by the way, is how you're going to memorize these formulas eventually, not this week. If you write it out, your brain will naturally start to remember it. It takes time. And then, so we got e to the x over 1. Of course, you do not have to write that over 1. And there we go. Okay. So what's different about 4? It might be a TOCO. Not necessarily. Okay, let me say something about this. Just watch me for just a moment. Don't write anything down. Okay, here I am. I'm a calculus student. I'm at where you guys are at today. Okay, I'm going to pretend I don't know anything else that I know. I'll say I'm a good calculus student. Like, I thoroughly understand everything we've already done. Okay, which may or may not describe you. But I'm going to assume that I don't know anything else that you haven't been taught yet. And if I'm looking at this problem, I'm thinking of all the different ways we've done integration. And so I'm thinking maybe just try normal u substitution. All right, because you're not going to know how the problem is going to work out. So if I thought this was normal u substitution, maybe I would let u equal the denominator. You don't have to write this down because I'm going to end up erasing most of it. Just watch this for a minute. Then what would du equal? Negative 2x dx. And the negative 2 is totally fine to go to the other side. Now, this x dx works with this x, but it doesn't work with the 2. That plus 2 is a problem. It's in the way. Now, if this was times 2, I could move it out to the front, but plus 2, I can't do that. So then I start over and I go, well, that didn't work. This is why I was telling you not to write this stuff down yet. Just watch. Okay, then I think, oh yeah, but now I have arc sine. If I'm just looking at the denominator, I start to set this up. I'm still don't write this down. Just watch. If I look at the denominator here, I can see that a should be 3, because 3 squared is 9. U is going to be x in the dx. But then I have this x. I don't like that there. The 2 alone would be okay, because if all I had was 2, I could move that out to the front. So all this to say, I don't want to deal with the x plus the 2 at the same time. It would be so nice if this only had an x or only had a 2. So I'm going to introduce you to a new strategy. It is the last one, which is I'm just going to split this up into 2 integrals. Then I'm just going to work each one individually. So I have the x over the denominator, have that integral. And then I have a whole nother integral for just the 2. Okay, so you can write this down. What's going to happen is one of these is going to work out like an old u substitution problem, and one of them is going to work out like the arc sine. How are you going to know this is going to happen? Because you go through the steps of figuring it out. It's not like you're going to look at a problem in 5 minutes and go, that's when you do this thing. Okay, you're not going to know that. It's just a process we have to kind of work through. Tomorrow, though, I am going to lay out everything we know about u substitution and integration, and we're going to look at it and kind of know when to do which thing. All right. Let's focus, excuse me, let's just focus on one integration piece. So this is the piece where if you let u equal the denominator, this is just normal, good old u substitution. Then du would be negative 2x dx. This was our first thoughts. The reason this works on this piece is because I have an x and a dx in both places, which you like. You want that to match up. The negative 2 I'm going to divide over. And let's think about how this gets transformed. So remember, I let u equal something that was under square root and in the denominator. So what's the power on u? Negative 1/2. The x and the dx gets replaced with the negative 1/2, which I already wrote, du. I'm going to keep going in this one part. So how do we integrate this? The old integration, we just add 1 to the power. So that would be a positive 1/2. And that's what it's going to go down there as well. Although you don't have to simplify. What is all this junk in the front? What does that tell you? What is that equal to? Negative. Negative 1 is fine. Okay, u would just be 9 minus x squared to the 1/2. And I could put a plus c here. I'm going to wait until I get the other piece, and then I'll just write plus c at the end, okay? We could go at it right here, though. That would be okay. Yeah.
Like when you had 1 over the square root, could you just go into ln of the square root?
You can only get natural log of u if you have 1 over u exactly. If it's 1 over u squared or 1 over square root of u, you can't do natural log. It's a great question. All right. So here we have this other piece over here that we got to integrate. So it's like 2 problems for the price of 1. Don't you feel like you're getting a discount here? All right, so, well, before I start with this 2, I don't really like this 2 here. So what could I do with it? Move it to the front, and then that just leaves a 1 there. All right, so then I have an A, a U, and a DU. This is all the stuff we kind of thought through at the beginning. So I'm kind of just going through that process. So my A is 3, U is just plain X, and DU is plain DX. So this ends up being 1 or 2 in the front, and then 1 or du even over square root of a squared minus u squared. This is arc sine. So I'm going to go arc sine u over a. Or arc sine x over 3. So my final answer, all of that. Just going to write it all together. If y'all love this one, you're really going to love the next one. Okay, but I will tell you, we're at the end of learning how to integrate new stuff. I mean, this is it today. There is lots more to learn, but not in Calculus AB. Okay? All right, so separating the numerator. That's something that we can do, and then it puts it into 2 integrals, and usually one of them is going to be like normal u substitution. One of them might be natural log or arcsine or arctan or something like that. Okay, let's look at the next problem. Number 5. Okay, what are our thoughts here? I'm hearing something about long division, maybe. Long division?
Nope. No.
This doesn't factor, although that wouldn't be maybe bad to try, although I'm going to tell you the ones I'm going to give you aren't going to factor. Long division is what we want to do here, because even if I did what I did on the last problem, which is split this up, I'm still going to have an issue with this x cubed. So we got to do long division. Yay!
Yay!
Okay. So let me remind you how to do long division. You take the denominator. If there's a missing term, put a 0x there. That just helps everything line up. That divides into the numerator. Now there's no x squared and there's no x. Excuse me. If you just hate doing this, you're not alone. If you don't know how to do it, just be like, today's the day. All right? Okay. X squared into 3x cubed. What is 3x cubed divided by x squared? 3x. And here's our check. 3x times x squared is 3x cubed. And keep multiplying. 3x times 0x, 3x times 4. You multiply whatever you write up here by all of this. So 3x times x squared, 3x cubed, 3x times 0x, 0x squared, 3x times 4, 12x. And then we subtract. We got to subtract everything, so anything down here, we got to change the signs. If it was a negative, we would change it into a plus. First term always cancels. If it doesn't, you did something wrong, go back and fix it. But it should always cancel. If you're lucky, the second term is also going to cancel. And then it looks like we're left with a negative 12x and a minus 2 once I bring that down. And that's it. I can't go any further because I ran out of terms. So that's how you do the long division. And that's really the, I mean, I could Katie code this, but there would be no point to that. This is the first step of a problem. You've got to be able to do this, and you can. It's just going to take some practice and asking good questions, which you guys are doing, so keep at that. This whole integral then, because that's really the first step, we're not done yet. This whole thing turns into 3x plus your remainder over what you were dividing by.
You just simplify that to minus 1.
Well, I'm going to do something else instead of that. She asked if I could pull that negative out, and I can. The problem is, I'm going to split this up even further. Okay, I'm going to go ahead and make the 3x its own integral, and that's going to be the easiest one to integrate. And I'm even going to go so far as to split that through right there, like how we did on the last one. So I'm going to go negative 12x over x squared plus 4 dx, and then also negative 2. And this is as difficult as they're going to get in this class. And I want to talk about how this type of problem can be assessed more than just doing everything. Because a lot of times on a test, you're not asked to do everything. You're only asked to show certain steps. So here, this would be a great multiple choice question. Which of the following integrals is equivalent to the integral that you started with? Well, a correct answer would be what I wrote over here. A correct answer would be this. What you also might see is something like these numbers getting moved in front. So that would be a way for me to test, do you know long division and do you know how to split up the integral? Okay, because what I'm trying to tell you here is I'm not going to test, I'm not going to test every concept of integration in one problem. Even if you understand all of it, there's just so many chances to make a mistake. It's not a good test question. So this is a way I could test, do you just know long division and how to split it up? Now, because this is notes, we are going to go throughout the whole thing. All right, the first one is easiest. What's the antiderivative of 3x? 3/2 x squared. If I was writing this on paper, I would probably highlight this, but since I'm doing this here, I'm just going to circle this in yellow. That piece is integrated. That's part of my final answer. I'm not going to do anything else with that. In fact, I'm not even going to write an equals here because I'm just going to do each piece individually. Okay, let's pick out green to do this piece. All right, so I know I can move the 12 out, the negative 12 out, okay? All right, so I'm going to go ahead and do that. Actually, hold on. I'm getting ahead of myself. A negative 12, though, can be moved out. It can be moved out to the front. Look at this middle piece right here, and let's think. Is this arctan? Or, if I let u be the denominator, will the du get taken care of right here? That's what I want to know. That x is kind of in the way. So I'm going to go out to the side. and I'm going to let u be the denominator. So then, what would du equal? This 2, just like always, we divide that out. So how could you rewrite that integral now? Yeah, so we let u be the denominator. Everything else was du. Let's keep going with this piece. We're just going to do one piece at a time. I'm going to go ahead and make that -6. You wouldn't have to, but that's fine if you do. Natural log of u, or -6 natural log of x squared plus 4. And there is the second piece. One more piece to go. So I've already told you this is as hard as it gets. This is as messy as it gets, and you will not have to be tested where you do all of this in one problem. But individual pieces are all good to go over. That's why we're going over them in our notes, okay? All right, so first of all, that -2, I'm going to move that out to the front. So essentially, there's really just a 1 up there. That makes this look more like the arctan problem. So off to the side, I'm going to do all my work here for arctan. This was the new stuff today. Some people get thrown off here because they're like, ooh, but it you know, a is supposed to be x. But do y'all remember what I said about a? It's always a number. Could you switch these two back and forth with a plus in the middle of them? Sure. A is 2 and u is x. It cannot be the other way around. It doesn't matter the order. A is the number, u is the x. Like I said, this problem has everything in it. Everything. So what we end up having is du over a squared plus u squared, which is equivalent to the arctan formula, which you can look up on the front of the page. So a is 2, arctan is arctan of x over 2. And that's the answer to the third piece. And of course, you could cancel those 2's out if you wanted. So the final answer, I just put it all together. If that's not a monster of a problem, I really don't know what is. Although I've definitely done harder problems than that, but that was part of, you know, later calculus classes, okay? The last one is actually way easier. Even though there's trig in it, it's much easier. And I'm going to make it even look easier by just changing one little thing. 1 minus sine squared would be cosine squared, and that would be a good thing to do, because that would make the problem easier. But do you see how the denominator is something squared plus something squared? I mean, you might not have noticed that at first, but do you see it now? This is the Arctan formula. So even if you didn't see it, just follow me with this. It's the last example we're going to do here. I know you're kind of wiped out, but we're going to keep going here. So what would the a equal? 1. The u would be sine x. The du would be cosine x dx, which is right up here, which is perfect. I'm going to move the 3 to the front. And I'm going to double check everything. I'm going to plug in a du in place of cosine x dx. This becomes a squared plus u squared. So see if you can finish this one out on your own. Go back and look at that formula if you need it. You can check your answer up here. And then I want to emphasize on the homework to skip number 5, and you can also consider 19 to be like a bonus. So if you're up for it, try it. If not, you don't have to do it. This homework is due Thursday. Did you guys